Hi everyone, and welcome to Erik's Electronics Workbench. So the project on the bench is this Hewlett-Packard 8664A RF signal generator. So this was manufactured in the 1990s. It weighs in at a back-straining 78 pounds, and it definitely takes up a lot of space on the bench. So the output is rated from 100 kilohertz to 3 gigahertz with a 10 millihertz resolution, or 0.01 hertz, which is a very impressive specification. But to take full advantage of the 10 millihertz steps, you need a very accurate and stable time base. So this instrument is equipped with option 1, which is a high stability time base option, so we should be able to take full advantage of the 10 millihertz resolution. Now alternately, you could feed in a 10 megahertz signal from an external time base or reference oscillator that's very stable and accurate. But no matter what the source, whether it's internal or external, you don't want the 10 megahertz reference to be drifting whatsoever, because if it drifts even slightly, then the output, even though the display will be showing a resolution down to 10 millihertz, the actual RF output would be slightly off from that value. Now, in addition to the main RF output, this has a low frequency output on this BNC connector. And it goes from 0.1 hertz to 400 kilohertz, and it has the same accuracy as the time base. Now, this signal generator has 2 internal modulation sources plus the external modulation inputs. And because it has the multiple modulation sources, it can create a subcarrier waveform. It also has a variety of sweep functions that are built in. Now, I already mentioned that it has option 1, which is a high stability time base, which is an oven-controlled crystal oscillator, also known as an OCXO. It also has option 4, which is the low noise option, and it has option 8, which is the pulse modulation and pulse generator. Now, this signal generator has extensive built-in self-test and calibration capabilities. Essentially, it can completely calibrate itself. There are a few internal adjustments that you would have to make for a complete calibration, but the normal calibration routine is all done in software, and essentially, again, the instrument can just sit there, calibrate itself, and you're ready to go. And the built-in self-tests are very complex and very extensive, and it can isolate the problem down to individual modules or defective cable, power supply issues, and so forth. So again, very, very extensive built-in capabilities. Now, when I picked up this signal generator, all I knew about it is that it was supposed to power up. And I did see a photo of it that the displays were turned on, but other than that, the operating condition was unknown. I was very interested in it because it has all 3 of those very desirable options. So I've already tried to power up the instrument, and when I powered it up, it immediately ran a very lengthy calibration routine, and then it showed a memory cleared or memory lost error, and briefly it showed an ALC OOL error, which is ALC is automatic level control and OOL is out of lock, so an ALC out of lock error. And those were put into the message queue. But neither error returned after the instrument ran for a couple hours. So they were just initially there, in the queue, but then they cleared out and were gone. So I haven't seen them return again for the first time that I ran the instrument. Now, the manual mentions that an ALC out of lock error can occur in certain situations and not necessarily be a hardware failure. Now, the memory lost error could be a dead battery, and this uses an internal NiCad battery. And I think it should be inspected and possibly replaced given the age of the instrument. It may have been replaced previously, but I have no history about this instrument, so we'll definitely want to inspect that NiCad battery. So if the battery is completely dried out and not working, it's never going to hold a charge. But the whole purpose of the NiCad battery is to hold up the memory. So when this does the calibration routine, the constants are stored in the memory. And when you turn the instrument on, normally it shouldn't run the lengthy calibration routine. It should just power up and be ready to go because it remembers the previous settings. Now, if there's drastic temperature changes that it detects, it will rerun the calibration process. So I'm curious to see when I turn the instrument on a second time here, and this has been sitting now a full day, if it's able to retain the memory or does it try and run the calibration routine again. If it does remember the settings and so forth, then I imagine that that battery is holding up some charge, but again, it probably should be replaced given the age of the instrument. I also noticed that there's a lot of dust in the fan vent, so really the instrument needs to be taken apart for general servicing and cleaning. So I'll take you through that as I disassemble it. We'll have a look around inside the instrument. The dust and kind of lint that was built up in the fan shows that the instrument probably has quite a bit of runtime on it. but that's just normal that that would accumulate, but that can cause cooling issues and other problems, and it really should be cleaned up. My intent is to have this on the bench and have it, completely working and be able to use it in future projects, and you'll probably see it appear in future videos if we can bring it around and have it back to full working condition. All right, so let's try and power up the signal generator. I'm going to turn on the main AC outlet right there, and let's see what happens. So this is the second power up. So that looks good there. Revision, self-test comes up, display test, indicator test on the keypad. All right, very cool. So that battery must be holding up because it didn't run the calibration routine again. And you can see right here there's an oven indicator because the oven is cold right now. So that will stay until the oven warms up. And that's the last frequency that I had typed in. So it is remembering the settings and the calibration. So that's very good to see. And I'm not seeing any errors. If an error were to come up and be put into the message queue, you'll see an indicator right here that says message. And if we press message, you can see the message queue is empty right now. Also very good to see. So currently there are no errors. So I'm going to let this sit for a little bit until the oven indicator light goes off, and then we'll continue with doing some initial tests and checking. I haven't checked the output. I have no idea, the operating condition. The fact that it does pass the self-test is a very good indication. It looks like it's fully calibrated with no errors at this point. So that's a good indication, again, that the signal generator is probably working reasonably well, but we need to take a look at the output. I'll put that on the spectrum analyzer and also connect it to the frequency counter. Let's kind of get an idea of the operating condition, see if there's any issues going on. All right, so the oven indicator has turned off. So I'm going to move the camera over to the spectrum analyzer, and let's take a look at the output from the signal generator. All right, here we are at the HP 8561E spectrum analyzer. So this spectrum analyzer was featured in 2 previous videos for repairs. So if you're interested in seeing those repairs, definitely check out those other videos. So I have the 8664A signal generator set to 1 megahertz at 0 dBm output. The RF is off, and I'll turn it on in just a moment. And also the modulation is turned off right now, but in a little bit I'll turn the modulation on and we'll take a look at that as well. So let's just step through several different frequencies and a few different amplitudes, just get a feel for how the signal generator is working or if any problems stand out. All right, so let me switch on the RF output. There it goes. So over here, I need to go to frequency, and center frequency should be 1 megahertz. And the span, let's make the span, let's say 10 kilohertz. All right, and do peak search. So that looks very good. So you can see on the marker right now, it's at minus 0.17 dBm, and there's about 6 feet of cable between the signal generator and the spectrum analyzer, so there'll be a little bit of loss in that cable, so no problems there. And the frequency looks to be quite accurate, no problems, sitting right at 1 megahertz. Now, keep in mind that for actually testing the RF output amplitude on the signal generator, you don't want to use a spectrum analyzer to check the actual calibration and see if it's within spec. You need to use a power meter and have the power sensor right on the RF connector on the signal generator, because there's some loss in the cable, very measurable loss in the RF cable between the spectrum analyzer and the signal generator, and you don't know exactly how much loss, so that's kind of an unknown. So you really can't rely on this value for the amplitude as an actual measured amount. You wouldn't want to try and calibrate using that or something like that. So again, you have to use an RF power meter, which I do have, and I'll connect that ultimately to this signal generator and take a look at the actual output just to make sure that it's within spec, because if it says 0 dBm output, it should be right on 0 dBm output or whatever it's set to. But again, this is reasonable because of some slight loss in the cable. All right, so I'm just going to step down on the amplitude here. So let's go minus 10 dBm, we want to go right there. Still getting used to the controls and layout on the front panel here. Okay, but that's fine, that dropped down. So on the spectrum analyzer, each graticule, the change is 10 dBm, okay, per division. So no problems there. Do another peak search. It's right on there, so -10 looks good. So if I just step this over like that, this should go to 20. Yes, it did. 30, 40, 50, 60, 70, 80, 90, and we're going to basically be down in the noise. That's a -100 right there. But yeah, that looks like that's working. No problems there. Let's go back over here. 0 dBm. So let's change this. Let's go to, say, 100 megahertz. So go frequency 100 megahertz. So let's go over here, frequency, center frequency 100 megahertz. Okay, so again, the amplitude looks fine. Frequency is pretty close right there. It's not exactly on 100 megahertz, but very, very close. Now again, with this signal generator, it should be sitting right on, spot on the frequency, and I'll connect it to the frequency counter. We'll take a closer look at the actual output frequency, but this looks very, very close here, and could be a slight inaccuracy in the spectrum analyzer, although it's quite accurate. It's been calibrated, but nonetheless, it is sitting quite close there, so don't see any major problems. But let's go over here. Let's try, let's say, 500 megahertz. Frequency, center frequency 500 megahertz. So again, the frequency is off just a little bit. I would expect that to sit a little bit closer to the 500. It's 499.99967. So, just off just a little bit. Amplitude looks good, so it's sitting right at -1 dBm, but again, very reasonable for any loss that would be in 6 feet of this coax. It's connected right here, so I don't see any problems with that. Let's jump up to, say, 800 megahertz. So frequency 800 megahertz. So again, pretty close, but a little bit off on the frequency. Amplitude looks fine. Let's go, let's say frequency 1 gigahertz. Peak search again. So consistently, the frequency seems to be off a little more than I'd like to see. Let's take a look here at frequency. Let's go to 2 gigahertz. So there's 2 gigahertz. So you can see the frequency seems to be shifting off a bit. Again, 2 gigahertz would be right in the middle. So I wonder if there's a little bit of inaccuracy going on, an issue with the frequency. Let's take a look here. Let's go to 3 gigahertz. So this is the maximum frequency here. See center, 3 gigahertz. You can see it's down just a little bit. I would definitely expect that to be sitting closer to the 3 gigahertz mark. All right, so let's take a look here at, go back down, let's try frequency. Just pick an arbitrary value. Let's go frequency 300 megahertz. Frequency 300 megahertz. And let's make the span, let's step this up to, say, 50 kilohertz, and I'll turn on the FM modulation. So let's try this, go FM, internal, needs to be on. And so we're going to modulate, it's a 1 kilohertz tone, and let's give it some modulation here. Let's go, set way too wide there. We need to step that down. Okay, so there's 10 kilohertz with a 1 kilohertz tone, 300 megahertz, and yes, it is modulating, so no problems there. Looks like that's working okay. And let's take a look here. Let's go turn FM off. And let's take a look at AM. Just try that. AM is on. So 50% AM modulation, 1 kilohertz tone, internal there. That is set. And yes, that looks okay. Let's take a look here. So yeah, the internal modulation for AM and FM appears to be working okay. In fact, this is, we can demodulate this. If we go over here, I believe it should be AM. Modulate that. Search, make sure it's on there. Go back over to auxiliary control, AM, FM. AM demodulation is on. Yep, there it goes. Get the microphone a little bit closer here. You can hear that. So it demodulates in a few seconds at a time, and while it's demodulating, then the sweep stops. So you can hear the tone. So no problems, definitely working correctly. All right, so very happy with those results, but that frequency seems off a little bit. So what I'm going to do is let's connect this signal generator over to the frequency counter, and the frequency counter that I have, let me turn this back down again here, has been calibrated against a GPS disciplined oscillator that's very, very stable and very accurate. So there's actually two ways that we can look at the frequency stability on the signal generator. We'll put it on the frequency counter and see what the actual value is, and then I'll connect it to an oscilloscope, and I'll show you how to take a look on the oscilloscope and compare against the GPS disciplined oscillator as a reference, and we'll compare that against what's coming out of the signal generator. So I'll show you both ways, and using the oscilloscope is actually more accurate to compare against any drift or change. Okay, so let's do that next. All right, back to the signal generator. You can see it's set to 10 megahertz at 0 dBm output, and I have it connected to the frequency counter. So I'll move you up to the frequency counter and take a look at the result. All right, so taking a look at the 5334B frequency counter, which was also in another previous video for some repairs and maintenance, and I show the calibration on that frequency counter. So again, if you're interested in those sorts of things, definitely check out that other video. But you can see the displayed frequency. So right now the signal generator is set to the display of 10 megahertz, but we're not on 10 megahertz. That's definitely off, and it should be spot on 10 megahertz. There's no way that it should be that far off. So definitely an issue going on. Something's not quite right, so I have to take a look at that. Now, if I go down here and actually make a change, so I'm going to start increasing this by, there's 1 hertz higher, very small increments, 2 hertz higher. So it's getting a little bit closer. Okay, right there, it's very close. Right there. Okay, so that's 6.6 hertz higher on the display. So I rolled the frequency up just a little bit, so 6.6 hertz. So once it's on that frequency, then it is very stable, but it is off from the displayed value. Now, something else that we can do, go back here to 10 megahertz, like that. And I'm going to move this down to the oscilloscope. So right now, this input on the oscilloscope is coming from the GPS disciplined oscillator. So this is spot on 10 megahertz, very, very accurate, down to a 100 microhertz resolution, okay? And that's the green trace that you see right there, the green waveform. Now, the other trace, which is not triggering and just moving by very, very rapidly, is the output from the signal generator. Now, if I trigger on channel 2, you can see now the blue trace is stable, but the other trace, which is from the GPS disciplined oscillator, is now just rapidly moving past. Now, if both of those are exactly at 10 megahertz, then they'll appear to both be stable. Okay, and if there's a very, very slight difference in frequency, then the waveforms will shift. Well, I should say the blue waveform, the one that you're triggering on, in this case from the GPS disciplined oscillator, will always remain stable because it's the triggered waveform, but the other waveform could drift ever so slightly if it's just a little bit off frequency. It can be off frequency by such a small amount that you wouldn't see a difference on this frequency counter, but you could see a slight drift perhaps over a span of, say, an hour or so, but it might drift just a little bit. Or if they're spot on exactly the same frequency, you would see no change between the two waveforms. All right. So now what I'm going to do is change this frequency back up by a little bit. So we'll go back up to about 6, right there, 6.6 hertz increase. And let's take a look. So now you can see very, very stable. So again, the blue trace is coming from the signal generator, and you can see how it's drifting just a little bit. So it's not exactly 10 megahertz, but it's very close, even though this was showing right at 10 megahertz at that point. There is just still a slight difference. If I move this over like this, so the reason that flickers when I change the frequency is because this signal generator mutes the output or turns the output off when you change the frequency. That actually, I believe, can be changed so that it doesn't do that, but that's by design that it's doing that. So I'm going to just nudge that a little bit there. So how does that look? Okay, so yeah, that's very stable now. Not really changing at all. Maybe maybe a little bit, trying to nudge that way, but not much. So now the displayed frequency is from 10 megahertz, it's increased by 6.58 hertz higher. When I did that, now you can see it really is at 10 megahertz. And you can see it's drifting again a little bit. I don't like that. That shouldn't be drifting at all. So, it sets in and was stable, and then we get a little bit of drift. It's very minor, but I would expect better than that. So I need to take a look and see exactly what's going on, because that's not quite right. Well, I have the oscilloscope connected. Let's take a look at the low frequency output. So what I'm going to do is make a couple changes here. So leave that alone on there. Let's take this off of here. This over like so. That. Let's take a look at this here. So channel 1, we're triggering on that. Let's display channel 1. Actually, take channel 2, turn it off. Channel 1, let's try that. So if we go to the audio frequency, I want to turn that on. All right, so that's 1 kilohertz. Let's see if we've got... Yes, we do. There it is. Okay, that's a very nice looking waveform. That looks great. So no problems there. We can actually move this back up here. So it's, again, very close to 1 kilohertz, but it's off a little bit because the other main frequency is off. So I'm not surprised to see that this is off just a little bit. But the waveform looks very, very nice right there. So no problems with that. So it looks like the audio output or the low frequency output is working okay. And while I have this connected to the oscilloscope, I'm going to move this back over to the main RF output. And let's just take a look at the waveform that's coming out of the signal generator just to make sure that it looks okay, that it looks like a nice clean sine wave. So I'll move this back over here. And let's go, it's still on 10 megahertz, that's fine. Speed this up. Let's go this way here. Yeah, very nice looking sine wave. So that's 10 megahertz, the main RF output. Looks very good. Let's try something higher. Let's say frequency 100 megahertz. Yeah, great, looks good. All right, top cover is removed, and look at that classic HP quality, so very impressive. So I cleaned out some lint and dust. Most of it was located along that front edge where the vent is in the cover. So the air is drawn through that vent, moves through the instrument, and then exhausts out the back by the fan. And over here you can see it says location A3 and there's an empty slot. So nothing's missing. That location is just not used on this instrument. So from what I can see, everything looks to be in good condition up in this top area. Now this section over here is where the battery will be located. It's on the main controller. So I need to remove this cover, some coax cables, and get access down in there. And by the way, there's two styles of covers that were used on these instruments. So this model has the two-piece cover, so the top and bottom are separate. There's also a single one-piece type of cover. So if you're working on one of these instruments, they might come apart different depending on the type of cover that the instrument has. So I started looking around a little bit, some of the cables, and thinking about the connections and the location of the reference oscillator, that option 1 that this instrument has. And I took a look at this block diagram right here, kind of thinking about that frequency error that the instrument is having and what could be done about that. And by the way, there are no schematics for these instruments, so they don't seem to have been released by Hewlett-Packard or Agilent. Later on, it of course was Keysight. So on the Keysight website, you can download the user manual and the service manual for this instrument, and the service manual has block diagrams and all the service troubleshooting and so forth, the built-in self-tests, the calibration, everything like that. So very useful. And there are a lot of block diagrams, but there are no actual schematics. And the schematics would have been in what's known as a clip. And the clip stood for Component Level Information Packet. And it would have been hundreds of pages long. And unfortunately, those aren't available. I've never been able to locate one for this instrument. So yeah, I don't think they were ever released. But anyway, on this block diagram here, this is the section for the time base or the reference oscillator. And you can see right here, bring this up a little bit closer, but they do show option 1, the 10 megahertz reference right there, and then here's the standard reference. And what they're showing is that the two would join together, and then we have an amplifier probably acting like a buffer. So over here it says 10 megahertz. Now this connection that's coming over here, I'm assuming would be inside the instrument because there's nothing on the back panel that says internal reference going in. There's an external reference, and that's this connection right here. So you can provide your own external reference time base. So I'm not exactly sure. I think again this would be an internal connection, and then of course you can see it goes over here and then through this switch, and that would be selecting if you're using the external time base or internal. This switch would select between the two. But going back over here again, if we're looking at the option 1, again this instrument does have that. This would imply that it's just all an internal connection. But I don't think that's actually how it's supposed to work. All right, and then over here you can actually see it says external 10 megahertz, which is, well, it actually says not used. But on this instrument, there is a 10 megahertz connector on the back panel. So I'll take you down to the back panel connectors in just a moment. We'll look at all of this, but a little bit confusing because it says it's not used, but it seems like it is on this instrument. EFC is electronic frequency control. So you can electronically control the frequency of the reference oscillator, but that's not normally used. I'm not using it for the purposes how I have it connected, but that connector is on the back panel. So again, I'm not so sure that this is actually how the instrument works, okay, with this sort of an internal connection. And if we take a look over here, something that I found in the service manual right here. So there's quite a few of these special functions, which are the front panel key that says special, and then you can enter a number. And if you don't know exactly which number you would use, you can just scroll through the actual text where it says reference source and allow external reference, things like that will come up on the screen, so you don't have to memorize these numbers. And there are many of these choices. But right here, take a look at this 161. It says reference source. Right here it says, this special function monitors whether the instrument is using its internal reference oscillator source or if an external time-based source is connected. And then parentheses, the high stability time-based option 1, which we have, is seen by the signal generator as an external time-based source to the rear panel reference in connector. When I saw that, I thought, well, wait a minute, that's not what's going on, because there is a reference in connector on the back panel and there's nothing connected to it. So I think the solution is to put a coax jumper between two of the connectors on the back panel. A very simple fix, but again, this is a little bit different from what that block diagram is showing. And this would explain why maybe it isn't even using the option 1. I don't think that that option 1, the high stability time base, is actually connected right now. And then right here it says 162 is allow external reference. It says this special function allows you to prevent the use of an external time-based source, and then parentheses, which would also affect the use of the high stability time-based option 1. When on the preset condition, so that's the normal setting when it's turned on, the signal generator may use the internal reference oscillator source or an external time-based source. And then up here they're talking about that the option 1 is seen as that external source. So unless this has been turned off, and I'll definitely have to check these and make sure that this is set correctly. But because the memory was lost and the battery, seemed to have wiped everything out, and I got that memory cleared error, I would think that these would reset back to the factory default anyways, but definitely want to double check this. And it says when it's turned off, the signal generator will only use the internal reference oscillator. So let me move you down to the rear panel connectors and we'll take a little bit closer look. All right, so here's the rear panel connectors. So when I received the instrument, all the B and C connectors had these dust covers on them. So starting up here, this says 10 megahertz out. This is voltmeter in, audio trigger. This says external reference in. You see option 1, and it's blocked in around these two connectors, so the EFC connection and then reference out. Right here it says X-axis, Z-axis. It says SEQ, I think it means sequence. I'm not entirely sure what that connection is for. These connectors over here are for the pulse modulation option, and of course the HPIB or GPIB connection. So taking a look right here, I did look at the back of the instrument when I first received it, and I saw this connection right here in this blocked in area for the option 1, and my first thought was that this is just a convenience for an output on that reference oscillator that you could use to connect to another piece of equipment, another instrument, maybe to synchronize, so you have the one time basis driving multiple instruments. But I'm not really sure that that's what this is for. I think this is the only output of the internal high stability time base. So it's not a duplicate second output, because I don't think, if we look right here, this option 1 where they show an internal connection right here, I don't think it has that, all right? So I think this is the only output right here. And if we look right here, this says 10 megahertz out. I think what that is actually this reference out right here, I believe. This says 10 megahertz right there. I don't think it's this connection, because I think this is an internal connection inside the instrument. There's no internal reference right here, that connection. There's nothing back here that's marked as that. And then right here, external reference in, that would be external reference right here going in, there. So it looks to me like this reference out for the high stability time base needs to be looped back over here to the external reference in. So I think these two need to be connected together with a coax jumper. So really a simple solution, but I overlooked that originally. I didn't realize that these two needed to be jumped together. All right, so I found this short coax jumper. So let's connect the signal generator to the frequency counter and see if the frequency accuracy has improved. All right, the oven light just turned off, so at least the oven is up to temperature, but the high stability time base probably hasn't completely stabilized until the instrument runs for a while. But nonetheless, the frequency accuracy looks very good now. So I think I should rerun the calibration procedure with the high stability time base properly connected. But you can see the RF output is set to 2,000,000.05 hertz. And let me move you up to the frequency counter. And take a look. So it's sitting right very, very close to the same value. So it's just about 10 millihertz off. we have a 0.04, and there's 0.05, so spot on right there, but very, very close. And again, the oven light just turned off, so looks very good at this point. Very happy with that result. Looks like the accuracy for the frequency has returned to what it should be. So I'm going to go back down again to the signal generator right here. And let's take a look at the audio output. I'm going to reach around on the other side of the camera right here. Turn this off. Just move this over there like so. So I have it set to 5 kilohertz. And reach around on the other side to the frequency counter, turn off the 50 ohm impedance, and move you back up to the frequency counter here. So it looks very good. So the accuracy, on the audio output is very, very close to what it should be. It's basically spot on. No problems there. That was definitely a ways off before, as we saw. So it looks like the frequency accuracy is working correctly all around now at this point. So I'll continue on with some disassembly, and let's take a look at the battery. All right, so I removed the cover that fits in this section, as well as the microprocessor board. And the microprocessor board contains that NiCad battery, so I'll show you that in just a moment. So with this area opened up, now I have access to clean out the dust that's accumulated on other circuit boards and components in that section. I also removed the board that fits along this area of the instrument. And all these ribbon cables plug onto that board, and among other things on this board, it's a lot of main power distribution. So you can see some very heavy gauge wire that comes up to this connector, so that's distributing the power across to those ribbon cables, and then the ribbon cables are going up to each module. So with this circuit board out of there, I have access down to the cooling fan and other components in the power supply section, so I can clean out the dust that's accumulated back here. Absolutely massive transformer in this corner. That definitely accounts for a lot of weight in this instrument. And take a look at this circuit board right here. So this is the board that fits on that back section. Right here, and I have seen this on other HP equipment. These are little status indicator LEDs right here, and you can see how they're leaning over. I think HP just got a little bit sloppy when they soldered those in. I don't think they got pressed over by accident. Someone with a heavy thumb could come in here and maybe press that down by accident if you're working in the instrument, but I don't think that happened. And a lot of times LEDs that are soldered close to a board like this, if you try to bend them, it'll just crack the body of the LED. And what you don't want to do is try and stand these back up, because if you do that, it'll definitely break them. So what I'm going to do is just desolder one of the leads on the back side of the board, and then heat the other lead, and at the same time just stand the LED back up, and then just resolder the other lead that I desoldered. And then all of them will stand up and look a little bit better that way. So again, I've seen the same problem before on some other instruments. It's not really a problem, they do work, but it looks a little bit sloppy when they're kind of leaning over like that. Also, I'm noticing that quite a few components seem to have 1998 date codes in the instrument, so that makes sense. It's probably about when the instrument was manufactured. All right, let me just touch this up a little bit here and then move it over to the NiCad battery. This is the NiCad battery right here, this little yellow battery. So it's just a 45 milliamp hour rating, so it's a very small NiCad. So right now I'm charging it up just to make sure that it has a full charge, and then I'm going to do a discharge test on the NiCad and see if it holds up. If it performs and meets its rated specs, then I'm going to leave it alone. There's no corrosion, it looks to be in good condition, so it looks to be a good quality battery. Probably original, but I'm inclined to leave it alone if it's still working okay. And again, if it holds up with the full rated capacity, then that means it's in good condition. But if it doesn't work and discharges very quickly and doesn't have the capacity that it should, then I'll definitely have to replace it. So I just noticed that on the shield covering that huge power transformer is a date of 5/10 of 1990. I think 1990 is about when this series of instruments was introduced. So I wonder if HP did a large production run of these power transformers and then just stored them in inventory and used them as needed when the instruments were built up. So just a guess, but the other components seem to have later date codes, so it would explain why this might be an earlier date code, because I don't think the entire instrument was manufactured in 1990. I removed the bottom cover. There's really nothing too interesting to see on the bottom of the instrument, but there was a lot of dust that had built up all over the bottom, mostly on the circuit board. So I used a vacuum and removed some of the dust, and then I took the instrument outside and I used a soft anti-static brush and some compressed air and finished up cleaning. So now it looks very good. I also spent some time cleaning on the top side of the instrument. It turned out very nice as well. All right, so I removed the fan because there was quite a bit of dust on the fan blades, and there's just no other way to clean the fan without removing it first. So let me just lift up these cables here, and you can see down inside there, the fan mounts right across here. So there's just 4 screws, and you remove those and the fan lifts out. There's 2 wires that plug onto pins for the fan motor. The pins are down in that corner. I know it's a little bit dark down in there, but you can see those power transistors for the voltage regulators. Some more transistors over here, and the large blue filter capacitors, and there's some more hidden over there as well. So quite a few very large capacitors in the power supply. Also, with that fan motor removed, I was able to clean some more down here. So here's the fan right here. So nice and clean, ready to reinstall. And the motor seems to be in good condition. You know, it was quiet when it was running previously when we were testing. You can see when I turn the fan motor, it's got rocks back and forth very freely. That's always a good indication that the bearings are in good condition. If you turn the fan and it stiff and you just have to push it around and it never rocks back and forth with that magnetism, and that's an indication that the bearings are probably shot. So anyway, that's looking okay at this point. And let me grab the circuit board right here, and this is the board. Turn it here. This had these LEDs that were soldered in crooked, so I've got those fixed up there. Looks a little bit better. Also touched up those as well. Those group of amber colored LEDs were a little bit skewed to one side. So just looks a little bit nicer. The board is cleaned up on the back side. So again, when I was straightening these out, I just desoldered one of the leads on each LED, and then the remaining lead that was still soldered, I heat that, and at the same time I'm just pressing the LED gently with my finger, you know, to stand it back up, and that way you're not actually bending the leads, because if you just try to force the LED and stand it back up, you'll very likely crack the body of the LED. All right, so let's take a look at that memory hold-up NiCad battery. So I have the battery connected to the electronic load, and if I just move the camera up here, you can see the test leads going up to the battery. So just going back to the electronic load. The load is not turned on at the moment, so I'll do that in just a second. So the battery is rated 3.6 volts, and it's been charging the better part of the afternoon, and you can see the displayed voltage is 2.811 volts. And since I hooked it up, it seems to be falling just a little bit. Yeah, you can see it just toggled down just a little bit lower. So 2 strikes against the battery already. It's not off to a good start. Now, again, the battery is supposed to be rated 3.6 volts at 45 milliamp hours. So 3.6 volts at 45 milliamps would be 80 ohms. So you can see the electronic load is set to 80 ohms right now, constant resistance mode. So that the electronic load is just acting like a fixed resistance of 80 ohms. All right, so I'll go ahead and turn the electronic load on. And yeah, look at that. The battery voltage just completely falls away. So it can't hold up at all. That NiCad has definitely seen better days. So that probably just cleared the memory as well because that battery voltage fell so low. So I'll probably have to rerun the calibration routine when the signal generator is completely reassembled. So I'll have to see what I can do to locate a new battery and get that installed. So this concludes part 1 for the Hewlett-Packard 8664A RF signal generator. And if you enjoyed this video, you can let me know by giving it a thumbs up. And if you're enjoying the content on this channel, don't forget to subscribe because there'll be many more videos coming up in the near future. And definitely stay tuned for part 2 on this signal generator repair and service. All right, as always, thank you for watching. See you next time. Goodbye for now.